Manipulator Jacobian. Next to rotation matrices, this is the most commonly used concept in robotics, and we will use this in several places. Here first we will talk about velocity kinematics and see where you get the manipulator Jacobian in velocity kinematics. Simply speaking, it's a matrix that relates end effector velocities with joint angular velocities. And if you recollect, we had a similar matrix relationship in our 2R planar elbow manipulator example, where we had gotten the end effector velocity. In that case, it was x dot and y dot as a matrix multiplied by q1 dot and q2 dot. That is really the vector of q dot, right? So that is nothing but the manipulator Jacobian. So here V0n is the velocity of the end effector, Vp, we were calling that P, right? But so velocity Vp, velocity of end effector, but expressed in the base frame or the zero frame, the inertially fixed frame, right? Q dot is the vector of joint angular velocities, and when you have a prismatic joint, then it's really not an angular velocity but it's a linear velocity, but for simplicity we will just say vector of joint angular velocities. And JV in this case would be, since in the general case the velocity is three-dimensional x, y, z component, and then q dot is always n dimensional. N is the number of degrees of freedom of the robot, or how many joints you have. So this will always be 3 by n. So one thing to note here is this is not necessarily a square matrix. Unless you have 3 degrees of freedom, then this would be a square matrix. But let's go one step further. So more generally, we are not only concerned with the linear velocity of the end effector, but also angular velocity. So we would write V0n, but also omega 0n, which is nothing but the angular velocity of the end effector, but expressed in the base frame. That's why you have the 0 here. And this I would write as JV and j omega, two matrices stacked on top of each other, but still multiplying just the q dot vector. So angular velocity will also have 3 components. So therefore j omega is also 3 by n, and together, both of them together is, strictly speaking, what is called the manipulator Jacobian. 6 by n, and this is the manipulator Jacobian. And when people say Jacobian, this is the matrix they are talking about. But sometimes, depending on the context, when they say Jacobian, they might be meaning only the linear part, the linear velocity part of the Jacobian matrix, and that, depending on the context, you will have to figure out. Okay, so the idea now is to see if we can figure out a general expression for JV and J omega. We have already derived a specific expression for the 2R manipulator, which, if you remember, had sines and cosines of the angle. So really this is a configuration dependent matrix, which means for a specific robot, depending on which configuration it is, this matrix will be different, right? So that is one important point to keep in mind. So let's get into the derivation. What we will do is we will use the DH system. So there was a certain standardization in the DH system, and we will use those same assumptions and that standardization to derive an expression here for this Jacobian based on that approach. And then we will just go through the derivation and we'll talk about what it means at the end. Okay, so first let's start with the angular velocity part because that's easier to derive. So j omega, and we will invoke the assumption that we used in the DH system. So we assume all rotations about the respective z axis. That is how we started off in creating the DH system, if you remember correctly. With this assumption, then either the relative angular velocity of link I with respect to link I minus 1, so at each joint the angular velocity that you see is either qi dot times k hat, and if you want to be more specific, you can say ki hat for a revolute joint, or in case of a prismatic joint, angular velocity will just be 0. So this is equal to 0 for a prismatic joint. So either angular velocity is just the joint rate of change of angle along the local z direction, or it is 0. It's one of these two. And then fortunately for us, the end effector angular velocity in terms of the base frame is nothing but all the angular velocities of all the joints added up together. You know, this is a property of angular velocities that when there are multiple rotations involved, the angular velocities can be vectorially added. So that makes it a little easier, but we still need to worry about a couple of things. One, all of these were with respect to the local z directions, but here everything needs to be expressed in terms of the base frame, the 0 frame. And how do you do that? Well, that's what rotation matrices are for. So you have to multiply this, you pre-multiply this with the corresponding rotation matrix to get the same thing expressed in the base frame. So that is one thing we will add here. And the other thing to add here is the fact that when you have a revolute joint, you have this, but when you have a prismatic joint, you have 0. You want to build that into the same expression. So that for that we will add a multiplier called rho. So let me write this down, and it will make sense to you. So you have rho1 q1 dot k1 hat, and in fact, instead of writing k1 hat, k1 hat would be still in one frame, so I would have to write r0 to 1 k1 hat plus rho2 q2 dot r0 to 2 k2 hat, and so on and so forth, going all the way to rho n qn dot r0 to n kn hat. Here the rows are just a simple multiplier where rho I is either 1 or 0, and it's 1 for a revolute joint and it is 0 for a prismatic joint. So this is simply ensuring that wherever you have a prismatic joint, that term will end up being 0, but otherwise this expression is general enough. And this whole vector we were pre-multiplying by the rotation matrix to transform it back to the base frame, but since qi dot, each one of the joint rates, is a scalar, I could take the rotation matrix inside. That's the only thing I've done. Now when I look at this, this is already in the form of something multiplying the q dots, right? q1 dot, q2 dot. So everything else, if I take out, that will be my j omega. So that gives me the bottom part of this already. So j omega is nothing but rho 1 r0 to 1 k1 hat, rho 2 r0 to 2 k2 hat, and so on and so forth, all the way up to rho n r0 to n kn hat. So each one of these is a three-dimensional vector, and there are n of these, and that's why I would get a 3 by n matrix. Now you can write a simple code to calculate this. Once you have dh parameters, the rotation matrices can again be calculated in using a standard subroutine, and then you can populate this very quickly. But fortunately, since this is such a standard calculation, there are subroutines and libraries already available online that you can directly use to do this. But this is just to give you an idea of where that comes from. Okay, so we have already figured out one piece of the Jacobian, but we are yet to do JV. That is a slightly harder part, but that's what we'll come to next.